Okay, just a small correction in this equation. This is minus. So this is minus. Basically, all these E minus H0s, H0 minus E's will be E minus H0. And just note that this picture over here, so-called the Feynman diagrams, is just a picturesque way of writing a mathematical equation. This picture and this equation, they are basically the same thing. And this curly line over here, it's not another particle moving between those two vertices. That is my curly braces. Okay, let's go back over here. This is the problem I would like to study. I have two states. Both of them contain only phi1 field. They don't contain any phi2 field. And I would like to calculate the transition amplitude between those two states. And the interaction I have is given by this term over here. And just also let's remember what these fields are. They are d cubed p divided by 2 pi cubed, 1 over square root of 2 omega p. Let me call these ai e to power I p dot r plus ai dagger p e to power minus I p dot r. And this state, phi1 of, let's say, k, this is defined as square root of 2 omega k, a 1 k dagger acting on vacuum, and phi 2, let me say, just call I.
I'm sorry, aren't those exponentials supposed to have 4 vector multiplications on top of that?
Well, this is in Schrödinger picture. The operators are time independent. You can just insert the time dependent ones also. But you see, I'm looking at the Schrödinger picture. And then I have phi 1, let's say k1, phi 1, k2. This is square root of twice omega k1, 1, square root of twice omega k2, 2, a 1, k1 dagger, a 1, k2 dagger acting on vacuum, etc. So these are the definitions I have. Well, let's start with the first term. Now this VFI will be the final state V, the initial state, which will be phi 1 P1, phi 2 P2, V is lambda d cubed P d cubed X phi 1 X phi 2 X phi 1 X phi 1 K1 phi 1 K2. This is the matrix element I would like to calculate. Now let's look at this operator over here, phi 2. Phi 2 field has such an expansion. Now this term in the phi 2 expansion annihilates a phi 2 particle. Well, if you look at this term, I don't have a phi 2 particle. So when A2, whatever the momentum is, acts on this phi 1 K1, phi 1 K2 state, this gives me 0. So now what I need to do is I just need to just put this expansion in this product, carry out the x integral, etc. So I don't want to write them all out. What I would like to do is first identify some of the terms that will contribute and some of the terms that won't contribute, and just write the terms I will calculate only the terms that will contribute. So I can already see, without doing any more computation, by just looking at this expansion and my initial state, if I annihilate the second kind of particle in my initial state, it will be 0. But similarly, let's look at the other term, this AI dagger. What it will do is it will create a second type of particle. With some coefficients. But now this state contains a phi 2 particle. So whatever the other phi 1 operator does, well, my final state doesn't contain a phi 2 particle.
Sorry, are the K labels correct? Are they K1, K2 for phi 1, right?
Yeah.
I don't understand how the creation operator acting on the second phi operator. There is no any phi 2 in the eigenket of ours, but somehow there arises in the eigenket.
So you see, what I mean by this state, I wrote it over here. This is what I mean by this state. So there are many ways of showing it. If you want to see explicitly the K2 modes, well, I can say, I can write this state, just the notation. All the numbers of particles having momenta K, this is just an infinite set. Most of them will be 0. Only 2 numbers will be 1 in this set. Stating that in all the available modes for the first particle, only the K1 mode and K2 mode will have 1 particle in them. And then zeros for the other set. Now, this notation will basically tell me that how many K-type particles I have, 1-type particle I have, and how many 2-type particles I have. So this symbol and this symbol, they basically are the same thing. I'm not saying that this phi 1 K1, phi 1 K2 is actually this product. I'm not writing this on purpose, because my Hilbert states are infinite products. So I don't show infinitely many of them. I don't show the phi 2 occupation numbers in this kit. I only show the phi 1 occupation numbers, 1 and 1. That not because there are no phi2 occupation numbers. All the phi2 occupation numbers are 0. If I act with A2 on that ket, then phi2, one of the phi2 occupation numbers will be 1. All the others will again be 0. Let's discuss with you after the lecture, because you missed the first hour on Monday. You see, go back to my infinitely many oscillator analogy of this field. I have infinitely many oscillators, and my states are specified by which oscillator is in which state. When I show such a state, what I actually mean is that only 2 of the oscillators are in the first excited state. All the other oscillators are in the ground state, so their excitation quantum number is 0. I don't write them. I only write the states, the oscillators that are excited. So what this A2 K dagger tells me is it will excite the phi2 kind of oscillator in my field. Now, if you go back to my matrix element, yes, I just looked at this phi2. In phi2, I have parts that will oscillate the phi2 part, that will annihilate the phi2 particle. Well, since I don't have any phi2 particle in the initial state, all the phi2 modes are in the ground state. If I annihilate them, I will get 0. And there are also the creation operators for the phi2 kind of particle. Well, that will create a phi2 particle in this field, in this state. Now, these phi1 fields, I'm not looking at what they are doing. I don't need it at the moment. Whatever they do, they will not change the number of phi2 particles. So if this creates one phi2 particle in this state, well, the others will not change, but the final state doesn't contain any phi2 particles. So their overlap will be 0. So I don't know to do any computation here. I can already say that this matrix element will be 0. So the first order perturbation theory tells me that, well, this process that I'm looking for, this process, doesn't happen at first order in perturbation theory. It might still happen in the second order of perturbation theory. So let's look at the second order of perturbation theory. Now, what is the second order in perturbation theory? This term. This didn't contribute. Here I have a summation over all n. So what will this do? So let's calculate this V and F. What is n?
Ni.
Hmm?
Isn't it Ni instead of NF?
Ni, yes. Ni. Let's look at what that will be. It's there I have an infinitely many sum. But I will see in a moment that only 2 states will contribute to that term. Only 2 terms in that summation. Well, let me write the lambda d cubed r out. This is my integral in the expression of the potential. What I have is, let me use the shorthand notation. I will look at P1, P2, phi1 or phi2 or phi1 or K1, K2. No, sorry. This is n. I don't know what that is yet. But I have already seen that just looking at this n, phi2 operator over there. There was the part that contained the annihilation operator for the phi2 field. It doesn't contribute. The creation part will contribute. So when I act with phi2 on whatever state the state phi1 operators create, that n should contain a phi2 field. So that n will be something, whatever that will be. something times a phi 2 field. I'm not writing the momentum or anything at the moment, but there will be a phi 2 field in that n. Let's look at the other terms. Let me just multiply. Let me just look at phi 1 r, phi 2 r, phi 1 r, acting on this k1, k2. What are the terms I have? I'm still not doing all the computation explicitly. I will be trying to pick up the terms that will contribute. What do I have? I have a1 dagger, a2 dagger, a1 dagger. Well, that will create a state that contains an a2 field and four phi 1 fields. Then I have, well,
I don't
Hey.
see how four. If
Hold
you
on.
said-
okay, you see, each one of these creation operators create a particle. Okay? So this will be K1, K2, K3, K4, phi 2, because this creates a K1 type particle, this creates another 1 type particle. I end up having 4 particles. This will create we had already said that this is the only possible contribution I have, so I definitely have a phi 2 field at the end. This will create a, let's say, K1 P2 phi 2. You see, this will annihilate one particle, one of that. So either K1 or K2 will disappear in the state. There will be a phi 2 field. This will create another 1 type particle. Then I have this. In this case, this will annihilate something. This will create another phi 1 kind of particle. When I look at this one, this will have, both of them will be annihilated. It will create a state which only contains a phi 2 kind of particle.
What's the physical interpretation, between first two states? One of them K1, K2, K3, K4. The other one K1, P2. P2 meaning it has some, has. When we quantize it.
Now let's look at what these mean. You see, I have my particles coming with momentum K1 and K2. Okay, this is my initial state. And then there's some interaction. This interaction, let's look at this one. It creates 2 new particles. So out of nowhere, I end up having 2 new particles of the 1 type and a 2 type particle. Of course, these still exist. So I ended up having with such an intermediate state. You see, my computation gives me this state. This is the first case. The second case, okay, I have K1 and K2 kinds of particles. This is then there is the V. After the action of V, I have one of them remains. It can be K1 or it can be K2. And there's another one. And also a phi field, phi 2. I will show phi 2 field with wavy lines. This is this term over here. This term, well, basically the same thing. Again, one of the particles remains as it is. The other one just disappears, but some other one appears, and the phi 2 field appears. In the third one, K1 and K2 will arrive. Both of them disappear, and I have a single particle. Now, eventually, you see, this is the first, in this expansion, I'm just calculating these V and I's. These are the states that might give me a non-zero matrix element for V and I. Eventually what will happen is I will only have these kinds of, you see, interactions. This will remain. So these vertical lines are where there's an interaction with the potential. Or this one. Only these two will remain at the end of the day, when I think both of the vertices.
I am sorry, how were we able to treat that as if K1 and K2 change the trajectories on the first diagram we drew, but on the second one, K1 still continues its primary trajectory?
You see, this is not a trajectory. I'm not following the particle. These are momentum eigenstates. They are plane waves. They don't even have a position. Don't give too much meaning on these pictures. These are just pictures, nothing else. Just pictures representing mathematical expressions. But what I mean by a continuous line, whether it's bend or wiggly or etc., what I mean by a continuous line is K1 appears both before the interaction and it appears after the interaction. That's the only meaning it has. Or here, why do I draw such bends? It's not the trajectory. I repeat, we are working with plane waves, which are not such nice wave functions, but we are working with plane waves. They don't have a position. Their momentum is changing. That's the only thing that will happen in these wiggly lines. And here, well, okay, I draw a wiggly line. Don't give too much meaning into these pictures. They're just pictures. That helps us remember what the mathematical expressions are. Okay, so, at least at this step, I don't see too much simplification. Let's try to just write down and calculate these. Let's say, for example, what will be the matrix element corresponding to this one? If my n what is this matrix element? Let's calculate it. I want K1, K2, K3, K4, phi 2 of K5. Since I just have one kind of particles, just one of the second type of particle, I'm not writing phi 1 for the one type of particle. Those K1, K2, K3, and K4 are the momentum of the first kind of particle. And then I have, if I want to get a non-zero matrix element over here, I have to look for, okay, where was my field? I have to take this part in all of the phi 1 and phi 2 fields. d cubed, let's say p1 d cubed p2 cubed, I have 1 over square root of 2 omega p1, 2 omega p2, 2 omega p3. These are just the measures. Then I have e to the power minus I, right? Yes. P1 plus P2 plus P3 dot R. Then I have a dagger 1 P1, a 1 dagger P2, a 2 dagger P3, and I have K1, K2. Okay, I have this expression.
P1 and P2 as variable in this integral, but in the upper case, we take them as, so these examples, we say A1 or A2, but they act on momentum, so A1 operator should also carry a label for momentum.
Sure. That's why I wrote it. Come on, I'm kind of being lazy here. This A1 operator, A2 operator, these operators all carry momenta. I sometimes write it uppercase up in as a superscript, subscript, as an argument, whichever seems to be reason to be able to fit in the limited space I have. But they all have momentum. They create a particle of a given momentum. So momentum is there. So this was kind of a shorthand notation of what I will end at the end of the day. So here at least this argument tells me that when I'm having this summation over n in my perturbative expansion, here, this term, when I have summation over n, in principle, I'm summing over all states. But already this VIN tells me that no, not all the n's will contribute. Only the states that have 4 kinds of phi1 particles and 1 phi2 particle, 2 kinds of phi1 particle and 1 phi2 particle, 2 kinds of, or just the phi2 particle, they will contribute in that summation. All the other terms will be 0. So that was the main idea, main thing I wanted to achieve at this discussion. Then, okay, I restricted my summation to only these 3 kinds of intermediate states. Well, the middle 2 are the same kind of states because I have 2 phi1 particles and 1 phi2 particle in that intermediate state, in both of them. Now let's look at this one. Now what I will need to do is I need to calculate K. This will be easier to calculate. Let me look at A1 dagger P1. Why will this be easier to calculate? Up to proportionality constants. This will be equal to remember, that's the definition of my state. What are the proportionality constants? Well, I have twice the square root of omegas. in these definitions? Well, you see, I have twice the square root of omegas in the denominator in my integral. So that is why they will cancel. Now, how can I calculate this? I need to move this creation operator all the way to the left. If I remove that all the way to the left, a dagger acting on a bra will just give me 0. I have to commute it one by one through each one of those. So what will that give me? Let's say this will be phi 2, k5. Let me just write a couple of terms only. A1, K1, A1, K2, A1, K3. If I just commute A1, K4 and A1 dagger P1, that will give me a 3-dimensional Dirac delta. Because if their momenta are different, they will just commute with each other. If their momenta is the same, that is the Dirac delta function I have. But then I have plus well, basically I will repeat the same thing. When I commute this one with this one, I will get a Dirac delta of K3 minus P1. And then A1 will move here. If I commute that A1, AP1 dagger with AK2, I will get another term with Dirac delta of K2 minus P1, and another term with Dirac delta K1 minus P1. And 3 AAs. So what will this be? This state will be Dirac delta of P1 minus K4, K1, K2, K3, phi 2. Dirac delta P1 minus K3, K1, K2, K4. Dirac delta of P1 minus K2. Dirac delta of P1 minus K1. This is what I will obtain. Again, up to some normalization constants, which will involve up to 2 pi cubes, because the commutator is 2 pi cubes times the Dirac delta. So each one of these terms have 2 pi cube. I can also show this picture using pictures. You see, what I have done is there is one term in this expansion where this A dagger is matched with K4. This is sometimes called contractions. This A1 dagger can be contracted with K4. Each contraction gives me a 2 pi cube times Dirac delta, and the contracted field is removed. And this sum is nothing but sum over all possible contractions I have. And so at least with this interpretation, I don't have to consider this, okay, I have to commit this one with this, it comes here, let me go in the next step, commit with the next one, etc. I don't have to carry out all those steps. I can just say that, well, eventually I will commute this with the creation of this state, creation operator for that state, then I will get a term where it commutes with this operator, and then another term with this operator, and I already know what the contributions will be. I can avoid some of the intermediate steps. Well, I can do, let's go back. Remember
What's
this.
the difference between P and Q?
Hmm?
Is it not the same thing?
What do you mean by P and Q? P and K.
P and K, yeah.
They're momentum. I'm just lazy finding different names for momenta.
I mean, P equals H bar K, right? Like, basically. Yeah.
H bar is 1. P and K, they are the same thing. They are the momentum of my particle, nothing else.
Why we are writing P then? I mean, instead of Q. Q. K.
Okay. Well, when you are solving problems, write all of them K. Yeah, you see, I have the initial states which I labeled as K, the final states which I labeled as P. Then I have all these momentum in the integrals. I have to give them some names. And, well, I stuck with P for their momentum. I mean, the other alternative will be, okay, initial particles K, final particles K prime. Primes get confusing. Well, labels 1, 2, 3, 4 also gets confusing, so it's just whichever one works for you. They're all momentum. Don't get stuck with the names. You see, here I'm integrating over momentum. Here I'm using the momentum as my label of my states. Okay, so now if I look back over here, the Dirac deltas are nice because using those Dirac deltas I can integrate over P's. Dirac deltas also come with 2 pi cubes, so they will cancel these 2 pi cubes. So what are the possible terms that I will end up getting? Well, I will have to contract this 2-type field with my phi 2. I don't have any other option. Well, these fields P1 and P2, well, there are various ways I can contract, but remember, okay, so this P1 and P2 I can contract like this. That is one option. Then I have the states K1, K2, matrix element with K1, K2. Great, that is non-zero. But, well, let me write it out. This should definitely be contracted with this. No, not that one. This should definitely be contracted with this one. It doesn't have any other option. I have terms like this one. This is one possibility. And I have possibility, then I will just have this is equal to, I have 2 pi cubes, Dirac delta K3 minus P1, Dirac delta K4 minus P2, and then I have K1, K2, K1, K2, which will be non-zero. So this is a non-zero contribution to this matrix element. Oh, sorry, there is also Dirac delta K5 minus P3. And also keep in mind that, okay, those are 3-dimensional Dirac deltas. Again, I will just ignore the 3. Let's see what this contraction will contribute. Now, there are other contributions like, this is one possible contribution. This is another possible contribution. This is, you are forced to do that. P1 is contracted with, let's say, K3, P2 with K4. And then you have these two are contracted. This is contracted with one of the K1s. P2 is contracted with here, then you end up having K4 has to be equal to K1. Otherwise, it will be 0. Okay, you can just label the terms. Let's just look at one of them. I don't want to calculate all of them because this term will not contribute. I will just get rid of it eventually. Now, with all these contractions, remember, this is what I'm trying to calculate. I have this integral. Then I have 2 pi to the 9th. Well, this will cancel all these 2 pi's. Then I have Dirac delta 3p3 minus k2, k5. Dirac delta p1 minus k3. Dirac delta p2 minus k4. And, well, that's all. Then I have each power minus I p1 plus p2 plus p3, or okay, I'm done. This will be my contribution. Like there are omegas factors, lambda factors, etc. But this will be my integral. Now, what else I have? Then I will end up having R integral will give me a Dirac delta of P1 plus P2 plus P3. They should all sum up to 0 momentum. And then I have, well, K3 plus K4 plus K5. This is what I will end up having. Well, this is in fact, and then I have this state. I started with K1, K2, and then I had this state K1, K2, K3, K4, phi 2, K5. And eventually, in the next step, I have to annihilate these extra particles somehow. But then I will get K1, K2, or some combination of K1, K2. But what I want to look for is the overlap with P1, P2. But since momentas are different, this will be 0. I don't get any contribution. Let's look at the diagrams. This is the diagram that I'm calculating now. I have incoming particles, K1, K2. Then this vertical line is my interaction vertex, my potential. And there are many terms in my potential. One of those creates 3 more particles. Doesn't touch these ones, but creates 3 more of them. Then I have another interaction term. You see K1 and K2 remains. And after this interaction, I only have...
What's the... we are writing the somehow wave like the phi 2 field.
This is phi 2 field, this is phi 1 field. I'm just showing them.
Okay.
I'm not giving any meaning to them yet. This is just a picturesque way of showing my mathematical equations.
Okay.
Nothing else. So, at the final state, I should have 2 particles. So my second interaction with my potential should destroy 3 of them. Well, it will destroy the photon, these 2 fields. Now, it can destroy the ones that it created, but then K1 and K2 particles remain as K1 and K2. Their momentum didn't change. but I'm looking for final states with different momenta. So the overlap will be 0. So there won't be contribution from this one. Well, of course, there are these cases. Let's say K1, K2 comes.
So if amplitude 0, this picture cannot exist, right?
No picture exists. It just represents 0. It doesn't contribute to your process. Fine, but it doesn't mean the picture doesn't exist.
I mean, yeah, but we can't see in CERN, right?
No, it's 0. Well, the other option, it might be that, let's say that you annihilate the second interaction with the potential, the second term, you see, we have these two terms. So this is V and I, this is V Fn. Now V and I, we are looking at the case where V creates 3 more particles. So it's in the case of V, I have all these options when I multiply all those terms. I have these terms in V, they will create 3 particles. But then the second V should annihilate 3 particles, but it can annihilate the particles that it had already created, but then it gives 0. Well, let's say that it annihilates these 3 particles, then I will have K1 and some K3. K1 is the initial momentum. I want all the momentum will be changed. It didn't change. So again, this is 0. Well, there is one option, to be honest. You see, in the final state, I don't have K1 and K2. I have P1 and P2. So K1 and K2 should be annihilated at some stage, either at the first V and I, or at the second V Fn. Now, it is possible that the second V annihilates this one, the initial and finals. Let me show it this way. It stops them, if you like. It should stop this one also, so you have K3 and K4, which should be P1 and P2. Now, this matrix element will give you P1 minus K3, P2 minus K4, or the other way around.
Why not the combination though? Why not the combination? P1 minus
But you see,
P1.
You see, the state you have at this point, remember, we are looking at V and I V, N, V, F. You see, what you see here is our N. What you see here is Vn. V acting on N, this V acting on N. And V acting on N is K3, K4. My final state is P1, P2. So either P1 is equal to K3 and P2 is equal to K4, or the other way around. Here, I'm not writing momentum conservation, by the way. It's not momentum conservation. I'm just saying that if at this stage I have one particle with momentum K3, another particle with momentum K4, One of this K3 should be P1, one of these Ks should be P1, the other one should be P4, or else the matrix element is 0. But this will still be 0. There will be any contribution also from this one. But then you see, okay, using more or less the same reasoning, let's look at this one. What will be the contribution of that one? I have K1 and K2. There will be this at the first vertex, at the first interaction with the potential, at the first action of the potential, there will be a single photon left, single second kind of particle will be left. Because the V will annihilate two fields and create one other one. And then at this vertex, that will be annihilated, and you have two fields will be created. Well, you see here, okay, now we will look at it later on. So this seems to be a viable possibility. Let's look at the other two options. You see, the other two options were at the V. One of the initial particles are annihilated, another particle is created. So those are what these two cases are. What we'll have diagrammatically? Well, I have K1 and K2. Any one of them can be annihilated. I will have more than one contribution because of all these commutations will give me more than one contribution, one term contributing to the sum. Let's just draw one of them. Well, this will disappear. And there will be a photon created. And there will be some other particle created. This will disappear though. So this will be the intermediate state. In the intermediate state, I again have two one-type particles and one two-type particles. All of them will arrive at the final state. Now at the second vertex, you see, K2 must be annihilated, but I'm already looking at, I already have terms where one phi1 field is annihilated, another phi1 field is created, so K2 should be annihilated over there. And I should have another field created. These will not be touched. The photon will be annihilated. This will not be touched. So I have two incoming particles, and there will be two outgoing particles with different momenta. This will contribute. So I have basically these two contributions. Now, for those who have seen some Feynman diagrams or would like to compare these two cases to quantum electrodynamics, you can say that one is the annihilation diagram. An electron and positron will annihilate each other, and then the photon will create an electron and a positron. The other diagram will be, well, one of them will emit a photon, the other one will absorb that. These are the two diagrams I have. You see, at this point, this particle is annihilated, another particle with another momentum is created. So it is what happens over here. K1 is annihilated, another particle with another momentum is created. And at the same time, a photon is created, this one. And here, the particle that was created by first V doesn't change, just goes straight. And the particle that wasn't touched upon with the first V is annihilated. This one is annihilated, and another particle is created with a different momentum. So eventually all these messy diagrams will become these better looking diagrams, let's say.
Can I ask something?
Sure.
These points are what you basically say that interaction happens at a time or interaction happens throughout the time.
You see, I'm doing time-independent perturbation theory.
Mm-hmm.
There is no time here, nothing.
So the release of photon happens at a time.
There's no time. Forget about time. There's no time. I'm doing time-independent perturbation theory. There's no time here.
In the diagram.
No, it's not
What's
time.
the intermediate step then? What's the intermediate step?
Yes, okay,
I
the
mean,
reason why...
Let me erase the time, concept.
Okay, you see, the reason why I'm keeping emphasizing that here I'm just writing a mathematical equation. The mathematical equation I'm writing is this one. What time are you talking about? Well, that is the time that somebody doing the computation, I start doing these computations from the right. That is my time, my computation time, the order that I'm doing the computation, if you like. But you see, in this equation, there is no time. But since I'm interpreting this as my initial state, this as my final state, I do all my computations starting from the initial state and evolving into the final state. Even these initial and final don't have any meaning, by the way. Don't have this time meaning. There's no time here. These are not time-ordered diagrams.
So these virtual particles, they're just a mathematical trick, right?
I didn't define any virtual particle yet. I will define it in our next lecture. The only thing I'm doing is I'm just calculating each one of these terms one by one. I'm just doing mathematics at this moment.
The mathematics of the right-hand side of the final diagram you wrote.
Yeah.
In there is time.
No. You see, there is no time. I'm doing time-independent perturbation theory here.
Actually, it has diagonal, right? I mean, diagonal, not vertical, has to be. You write, you draw that.
You see, again, I repeat, there's no time here. Don't read these diagrams with time. We will do that eventually, but not yet. There's no time here. Thinking in terms of time simplifies our imagination. That's correct, but there's no time here. What I'm calculating here is, let me look at this VIN. That is my first thing. But when I say first, it's already a time, implying time. That's what I'm used to, what you are used to. That's why we try to interpret all these in terms of time, but there's no time. I will emphasize it again and again. Now, I'm just looking at VIN and saying that, oh, in this VIN, my potential annihilates a particle and annihilates the particle 1, let's call it electron, annihilates the electron and creates a photon. That is why I show it like this, as if there was a time. Oh, here the electron is annihilated, another electron is created, and the photon is created. And then I say, okay, there is this propagator. What is well, nothing really, it's just a name that I give to it. Oh, then there is this one that annihilates this photon later on in my computation, to be honest, not in the actual time. Later on, there is this one, this vertex, and which annihilates this photon, annihilates the other electron, and then creates a new electron. Now, if you read your Schwartz book, he talks about advanced and retarded propagators as if there is time. And then there is this paragraph where he says that, okay, this advanced and retarded doesn't really mean anything. It's just my convention. You could have just exchanged advanced and retarded with each other, so it doesn't make any difference.
But this creation and annihilation occurs at a particular point in space, right?
Yes.
So,
And what does he mean by this particular point in space is, let's look at our potential term, interaction. This is our interaction. You see, all these fields are acting at the same point. If I don't go to the momentum space, all these annihilations and creations happen at a given point. When I go to the momentum space and talk about the annihilation and creation operators of particle with definite momentum, no. And even here, I'm integrating over R. There's no really a particular point where these annihilation and creations happen. They can happen at anywhere, and I'm summing over all of them. Again, I repeat, these diagrams, you see, these diagrams that we will be drawing, they are not the trajectories of particles.
what I'm asking is this, what I was trying to get. Since this happens at a particular point, when we talk about field theory, how can we be sure that these expressions are Lorentz invariant?
We will come to that. You see, I'm using Hamiltonian. They are definitely not Lorentz invariant. I can assure you that they are not Lorentz invariant. They are Lorentz covariant. Now we will calculate the final state expression. And in fact, the reason why we will prefer to work with the Lagrangian rather than the Hamiltonian is that if the Lagrangian has a symmetry, unless there are anomalies, the results will have the symmetry. So that's why we prefer Lagrangian in field theory. But here I'm using Hamiltonian, so it's not invariant. I will be talking about the energies of the particles which are not invariant. But at least part of the final expression I will get will be Lorentz invariant. We will see. In fact, that is why we are keeping inserting the square root of 2 omega factors in P integral in the normalizations, etc. So at the end of the day, everything turns out, well, not everything, but the things that should be Lorentz invariant turns out to be Lorentz invariant.
Where is U channel?
What do you mean by channel?
I mean, this is the S, T.
What do you mean by S? What do you mean by T?
These Feynman diagrams we drawn.
Okay, I mean, if you would like to call that a W channel, fine, there's no problem with me. I didn't define them yet. It's just a name, which I didn't yet define.
Can I ask something?
There's another question, yes.
There is that operators have both labels for their momentum, which define. So there's both for a harmonic oscillator. There's a particle label. There's, for example, 5 particles, and 5 of them have a label for their particular ladder operators. And there's different harmonic oscillators, which also gives labels to ladder operators.
Yes. We have infinitely many oscillators, so we need to have infinitely many labels. Most of them will be 0.
And each of them have their own, for each particle in that harmonic.
We have different ladder operators or annihilation creation operators. You see, that is why I have this AK, dagger AK. K is their label, and it's continuous. I have infinitely many annihilation and creation operators.
But if we say AK1, it means another particle or another harmonic
Now,
oscillator.
AK, since I have 2 kinds of particles here, I just prefer to label them 1 and 2. I have this AK1 dagger, and then I have AK2 and AK2 dagger. I have 4 annihilation creation or 4 ladder operators. In fact, 4 types of annihilation creation operators, let's say, and there are infinitely many of each one of them. Because K can take any value. And for each K, there is a different operator. In fact, if K is different, they even commute with each other. They are so unrelated to each other. Well, and hence the notation becomes messy. So you will have many indices, many labels, and each one of these labels, some of those labels at least, can take infinitely many possible values.
Would we ask the question actually, when we're writing the delta function for the third, that one. Why the combination is not, P1, K3? Why the combination doesn't?
There are both of them. Well, for the time being, it will be with a plus sign. Later on, there will also be minus signs there. Both of them are there.
Are we doing problems on Monday or
Yes.
Monday?
Problems on Monday.
Why this gives here no contribution?
Which one? This one. This one doesn't. Well, let's see what this diagram will be. You have other momentum conservations. Probably this will not satisfy it. Well, I don't really see it now. Either you won't be able to satisfy some momentum conservations at certain places, or this will give contribution, but it will be what we call a disjoint diagram. No, this is not a disjoint diagram, sorry. What this happens is, we have K1.
After
Let's see.
the first vortex, you don't have momentum conservation.
You see, you have K1, then you have K2, and then you have the creation of 3 particles at a point. And then, let me draw it this way. It is this diagram. Right, K1 and K2 will be destroyed at the second vertex here. And K3 and K4 will be created at this vertex. And so here you have P1, here you have P2. So what are the conservations? We have K1 plus K2 plus K gamma should be 0. And also P1 plus P2 plus P gamma should also be 0. The first one is the momentum conservation here. The second one is the momentum conservation over there. We have 3 momentum conservation at each vertex. But this tells me, does this tell me anything? No, this is K gamma, sorry. No, it seems that this might be non-zero. But this will be, in fact, I think this will be non-zero. No, this will be non-zero, sorry. In fact, this diagram and this diagram will be added, just like this diagram and this diagram will be added. You see, these 2 diagrams will be added and give us what we call a Feynman propagator for these 2 propagators. These 2 diagrams, this one and this one, will be added to give me the Feynman propagator for this diagram, for this annihilation diagram. It won't be 0.
What's the line at the bottom?
In which one? This one or this one?
No,
This one.
above. The one that you were reading.
This one.
No, on the left.
This one.
Yes, in that one there's a line. Is that a state or
Which one?
right above BFM?
Oh, no, this is VFN. This is what I will see if I look at my computation at that stage.
And there's a line crossing.
There's a line, horizontal line.
Yes.
This one, or this one?
The last.
Well, this is what I use to emphasize. I cannot show my point. I cannot finger point. That is the only thing I don't like about lecturing on tablet. I cannot point easily.